Let's have a look at number 35. On number 35, we're launching a ball at an angle of 55 degrees above horizontal from ground level at 1.70 meters per second times 10 to the third power. Well, I'm going to go ahead and convert that to 1700 meters per second. Like most projectile problems, the first thing we need to do is solve for the x and the y components. So v sub x initial for the x component and v initial for the y component. Well, for the x component, since it'll be adjacent, we'll use cosine of 55 equals vi sub x over the hypotenuse, 1700. We multiply 1700 to both sides, and for the x component, we get 975.08 meters per second. For the y component, the exact same thing, only now this is the opposite side, so we use sine, so katoa, the initial sub y over 1700. And for the y component, we get 1392.56 meters per second. Alright, there's many different directions we can go from here. I'm going to take a more conceptual approach. Since the ball is launched at ground level and has a y component of its initial velocity at 1392 meters per second, we know if it's launched straight into the air and comes back down in the exact same place, it's going to have the exact same magnitude of velocity, only flip-flopped. So it's going to be negative, this value. So I'm going to plug it into this equation right here. And using that conceptual understanding, we can solve for the time first to make it a little bit easier on ourselves. So the final velocity will be exactly the same magnitude, only negative. So negative 1392.56, and that equals our initial velocity we just solved for, which was the y component, 1392.56. In the y-axis, we always have gravity that's acting on it. That's acceleration, so minus 9.81, and then times t. Subtract this over here to the other side. That gives us 2785.12 equal to negative 9.81 t. Divide out gravity from time. And then for time we get, and this is the answer to B, 283.91 seconds. Okay, for the ball's range, we want to know how far it's going to go before it lands. So in the x component. It's important that we understand that in the x component of motion, there's no acceleration. Gravity only acts on the y component. So our velocity in the x component is constant. Since we know the time, we know that we started our coordinate system at 0. We can use this equation right here and solve for xf, which will be the ball's total range. So xf equals 0 plus our velocity in the x component we solved for initially, 975.08. We just solved for time, 283.91 seconds. And we multiply that into our calculator. We get the ball's range. I'm going to use it down here, such a long number. 276,834.96 meters. 36, we have a fellow 52 meters above the water on a ledge. He's going to kick a stone off that ledge with a velocity of 18 meters per second. Two parts to this question. A, how long is it in the air? And B, what speed does it strike the water? Well, we can't solve for time using this equation just yet because we don't know the final velocity. We're going to use the y-axis only to solve for A, how long is it in the air? It doesn't matter if this is going 18 meters per second or dropped initially from 0 meters per second horizontally. They're going to fall at the exact same speed because gravity is going to accelerate both at the same rate in the y-axis. So let's use this equation to solve for the final velocity of the y component, and then plug that into this equation to solve for the time altogether. So Vx squared, what we're going to solve, equals Vi squared plus 2a change in y. We're looking for this. The initial velocity, even though it's going 18 meters per second, that's all horizontal. We've got to make sure we keep our components separate. In the y-axis, it's not moving up nor down starting off, so an initial velocity in the y component, the y-axis, is just 0 squared, plus 2, acceleration is gravity, negative 9.81, and then change in y is y final minus y initial. Its final position is negative 52 meters where it started. Initially it's 0, so it's just going to be negative 52. We plug that into the calculator. We get Vs squared is equal to 1,020.24 meters. To get Vf all by itself, and you take the square root of each. Vs squared, and because it's traveling down, it's going to be negative, right on the dot, 32 meters per second. We're halfway there. Let's plug this into this equation, still in the y-axis, and we'll solve for the time, which is what A is asking. Negative 32 equals 0 minus 9.81 t. Divide that negative 9.81 on both sides, and we get a t value of 3.26 seconds. Now, what speed does it strike the water with? We'll make some room here. We've got both variables. When it strikes the water, we're going to use the x component and the y component. And if we have the x component going this way, the y component going this way, we're looking for that resultant vector. So the y component, the final velocity the instant it strikes, we just solved for, is negative 32. The x component didn't change from its initial velocity because there's no acceleration acting on it. It's 18. So we'll take 18 squared plus negative 32 squared equals our resultant vector, which is, we'll call it d squared. Well, we better call it resultant vector because it's not a displacement value. And when you take 18 squared plus 32 squared, you get r squared. Take the square root of that. What the speed is? Remember, speed is a scalar. We don't need direction. We just need magnitude. 36.71 meters per second. All right, number 37 is another fun one. We have a daredevil who's getting fired out of a cannon at a 45-degree angle with an initial velocity of 25 meters per second. They're going to have a net 50 meters away from his launch point, and they want to know how high it needs to be to catch this fella. Well, the first thing we need to do is we need to break down our initial velocity, which is on a 45-degree angle, into an x and a y component. So, velocity initial x, velocity initial y. X is adjacent, so we'll use cosine, and we'll go ahead and jump that step. Since 25 is our initial velocity, we could say that vi sub x would be 25 cosine 45, which would give us 17.68. And then vi sub y would be 25 sine 45, because it's the opposite side, which would also be 17.68. Now, we're given this 50-meter measurement from the time he's launched to the time the net catches him. Since the x-axis, there's no gravity acting on him, we know that velocity is going to be constant. Both these are meters per second. We know that velocity is going to be constant. So, let's take 50 meters, and we'll divide 50 meters by our 17.68 meters per second to find how long it's going to take him to reach that 50-meter point. We divide 15 by 17.68. This is in the x-axis now. Remember, because there's no gravity in the x-axis, there's no acceleration, we can use this little trick. This whole thing is going to take 2.83 seconds. That means it takes you 2.83 seconds if you're traveling 17.68 meters per second to travel 50 meters horizontally. Now, we can use this to our advantage now. Now, we want to find out what his final velocity is. We're going to go to the y-axis. Now, on the y-axis, what is his final velocity going to be after those 2.83 seconds? Okay? So, we're going y-axis now. So, gravity comes into effect. So, Vf equals Vi plus At. Because we already found the initial velocity in y. We know the acceleration rate's gravity. We just solved for time using the x-axis. So now let's find what V final for y is. So 17.68 minus 9.81 times 2.83. Just plug and chug that. We get a final velocity of, this is in the y-axis now, negative 10.08 meters per second. Okay, now we have the initial, we have the final velocities for the y-axis. Now we use the Vf squared equals Vi squared plus 2a change in y, and that change in y is actually going to be the answer to how high our net needs to be to catch old buddy. So, Vf squared equals Vi squared plus 2a change in y. Remember, change in y is Yf minus Yi. Well, since the Yi stands for y initial, he's starting at 0. This doesn't matter. So we'll say change in y, or we could change this. Let's go ahead and do that. We'll change this to y final. And that final y is actually going to be the height. That's the height he's going to land at. He's going to finish there. Since this is negative, we know he's actually coming back down. So we know the path is something like this into the net. Final velocity squared, that would be negative 10.08 squared equals initial velocity squared, which is 17.68 squared. I'm going to go ahead and multiply these two. This is negative 9.81. So 2 times that would be negative 19.62, and y final for his final position. All right. If we square both of these, this ends up to be 101.61. This ends up to be 312.58. We'll have to subtract this one from this one. So I'm going to go ahead and jump that step ahead. So this squared subtracted from this squared, and then minus this squared, leaves us with negative 210.90. So I'm running out of board there, so I skipped those steps. I squared this one, I squared this one, then I subtracted this one from this one. Leaves you with 210.90, it's negative. And that equals the negative 19.62 y final. Now I just divide out negative 19.62. Negative 19.62. And our final answer, the height that this net needs to be to catch our daredevil, ends up to be 10.75 meters off the ground.